Hello, we're solving October-November 2021, variant 419702, variant 41 or 43 today. It's the same variant actually, it's identical. So it's variant 41 or 43, it's the same. Okay, so this is physics 9702, variant 4143, October-November 2021. This was also quite difficult, just like the October-November 2021, just like October-November 2021, variant 42. That was more difficult though. 4-1 is a bit easier. Let's begin. So I'm uploading this before the day of your exam. It's tomorrow, 10th May. Good luck. So why was this year a bit different from the other ones this session? Question number 1 typically starts with gravitational field. They gave centripetal circular motion for some reason. Okay. So you need to be prepared for this as well. Let's begin. With reference to velocity and acceleration, describe uniform circular motion. So what do we need to talk about here? We need to say that there is constant speed or constant magnitude of velocity. Okay, so we either say that there's constant speed or constant magnitude of velocity. That's your first marking point. So there's constant speed or constant magnitude of velocity, but remember the value of velocity changes because it's a vector quantity and velocity changes due to change in direction of motion. Okay, that isn't a marking point, but I just wrote that to explain things. You don't need to write this. Okay, so that's the first marking point. What's the other one? Acceleration is perpendicular to velocity. Acceleration is perpendicular to velocity. This is the second marking point. Acceleration is always perpendicular to velocity. Okay, so what if they give you another question? There's another variation to this, the one we saw in variant 4.2. What if they just ask you what is meant by centripetal acceleration? You're going to say it's the acceleration which is perpendicular to velocity. Now, if they ask you with reference to velocity and acceleration, describe circular motion, you need to talk about these 2 points. Okay, let's look at the next question. Two cars are moving around a horizontal circular track. One car follows path X and the other follows path Y as shown in figure 1.1. This is the start and finish line. So one of them will follow X, the other will follow Y. Now the radius of path X is 318 meters, path Y is parallel to and 27 meters outside path X. Okay, so what's the radius of path Y actually? It's 318 plus 27, which is 345. So basically the radius of path Y is 345 meters. Okay, so that's it. Both cars have mass 790 kg. The maximum lateral frictional force that the cars can experience without sliding is the same for both cars. Interesting. The frictional force is the same for both cars. So you guys need to understand something. While moving on the track, so this is a track, right? This is the car, it's moving. It will experience centripetal force that is perpendicular to its velocity or towards the center of the circle, right? So what actually provides this centripetal force? One component of friction actually provides this. If the road is banked, okay, typically friction provides the centripetal force when a car is moving on the road. All right. So find out the maximum speed. Okay, the maximum speed at which the car on path X can move around the track without sliding is 94 meter per second. So basically here we need to state that friction is providing the centripetal force, right? The friction F is providing the centripetal force. So F is actually equal to mv square by r. The mass is 790, the velocity is 94 whole square, and the radius is 318 meters for path X, right? Now, if you calculate this, you're going to get a value of 22,000. That's it. So since my data is to two significant figures, like look, I have three SF values, like 318 and 790, but I'm still choosing two. Why? Because the minimum is 2. Now let's move on to this table. This was a difficult one, this table. How do we answer this? It's going to be the same as greater greater. Y has greater than x. Y has greater maximum speed than x. Y takes longer compared to x to complete one track, but the centripetal acceleration is the same. Both cars move around the track. Each car has the maximum speed at which it can move without sliding. Complete table 1.1 by placing one tick in each row to indicate how the quantity is indicated for the car on path Y compare with the car on path X. Okay, so let's see. Basically, the key point here was this line, which we might have overlooked. Both cars have the same mass of 790. Also, the maximum frictional force that the cars can experience without sliding is the same. And we know that friction is providing the centripetal force. So, for both cars, the centripetal force is the same. That's the main logic, okay? So, for both cars, friction is the same, right? So, their centripetal force is also the same. So look at this. We know that centripetal force is equal to mv square by r, and this v square by r is our acceleration, right? So since the value of centripetal force is constant and both of the cars have a mass of 790 kg, which is also constant, the value of centripetal acceleration must also be constant, right? Since mass and centripetal force are constant, friction are constant, right? So centripetal acceleration is also constant. That's why the first arrow is the first tick mark is here. Okay, next. Um, Maximum speed, right? So this is a bit tricky. How does the maximum speed of y compare to x? What's the difference between y and x actually? The centripetal force is the same. The mass is also the same. What's different? The radius of the path, okay? So centripetal force can be written as mv square by r or m omega square r. mv square by r or m omega square r. So here's the thing. Centripetal force is equal to m omega square r. So the value of Fc and m are constant. So the value of omega square r has to be constant as well. So omega square r is also a constant. Now think about it. If since y has greater radius, the value of omega square will be less, right? Because this value is a constant. Now we know that v is equal to omega r, right? We know that v is equal to omega r. Okay, I can show you time first. It doesn't really matter. Let's deal with this step by step actually. Wait, I'm going to show you the best route. Let me just erase this for a bit. Okay, so we don't really need to bring omega in right now. We know that centripetal force is equal to mv square by r. This is constant and mass is also constant. So v square by r is also constant, the centripetal acceleration basically. So if you want to look at radius, right? we need to keep this value constant. So for y, since the denominator is greater, the value of the numerator must be lower. That is for y. What about for x? It's also v squared by r, but since the value of the denominator, wait, sorry, for y, since the radius is greater, the value of velocity must also be greater, right? To keep things the same. And for x, since the value of the denominator is less, the numerator will also be less to maintain that constant value, okay? Hopefully you understand. So I'm going to go again. Let's start from the top. Mainly, both of them have the same mass and the same friction. The friction provides the centripetal force. So we know that centripetal force is equal to mv squared by r. Since fc is constant and m is also constant, the value of v squared by r, or acceleration, is also constant. Now, since acceleration v squared by r is constant, since x has a lower radius, the value of the numerator will also comparatively be lower, because if it was higher, there was no way that this would match with the one for y, because y has a bigger radius, right? So if we increase the value of the denominator, the value of the fraction would have decreased. So how do we make sure this balances up? Both the numerator and denominator have to be higher to balance the lower radius and lower speed of x, okay? Now what about the time taken for one lap? Okay, now we should use this formula, the one for m omega square. This is also another formula for centripetal force. So omega square by r is constant for both of them, right? And we know that omega can be written as 2 pi by t. So 2 pi by t whole square into r is a constant. Now just think about it logically. Here's the thing. This value has to match 2 pi by t whole square into r. This must match for both of them. So since x has a lower radius, the value of this whole thing will decrease, right? Since r has a lower radius, but like x has a lower radius, but for y we actually have a greater radius, okay? For y we have a greater radius, so the value would inherently be greater. Now how can we make sure we balance this? What can we do? We need to ensure that this value is greater, this one, and similarly this value is smaller. Then it will cancel out, it will balance. How can we ensure that? Basically, to make this value greater, the denominator has to be higher, and to make this value smaller, the denominator has to be greater, and to make this value, the pink one, greater, the denominator has to be lower. Then everything else will cancel out, okay? Because ultimately 2 pi is a constant, right? What do we end up with? 4 pi square by t into r. We also end up with 4 pi square by t into r. By t square, I mean. Now 4 pi square is cancelled. We need to make sure that this adds up. Radius of y divided by ty square is equal to radius of x divided by tx square. So since the radius of x is smaller and the radius of y is greater, to balance things out, we need to ensure that ty is also greater and tx is also smaller. So how does y compare to x? Y will be greater than x, in fact. So this is a bit complicated. Make sure you learn the whole thing properly, okay? This was quite complicated. So in general, remember this. You can memorize this if you want. If you have the same mass and same frictional force or centripetal force, and if you're located at a further distance from the center, you will have the same centripetal acceleration, right? But you will have a greater speed and you will take longer to complete one lap, because obviously you need to travel a greater circumference, right? Make sense? Moving on to question number 2. Define gravitational potential. So it's the work done in moving unit mass. It's the work done in bringing or according to the Marx scheme, the best way to say this is it is the work done in moving unit mass from infinity to a point in the field. You can add this, okay? It's good to add it. It's a more complete definition. Let's move on to question number B now. The Earth E and Moon M can both be considered as isolated point masses at their centers. The mass of the Earth is 5.98 into 10 to the power 24 kg, and the mass of the Moon is 7.35 into 10 to the power 22 kg. The Earth and the Moon are separated by a distance of 3.84 into 10 to the power 8 meters, as shown in figure 2.1. So P is a point on the line joining the centers of E and M where the resultant gravitational field strength is 0. Point P is at a distance x from the center of the Earth. It can be moved between the Earth and Moon. So I always tell you this, but remember, since they don't have the same mass, the mass that is smaller, right? The neutral point will be at a point that is closer to the smaller mass, the Moon. Remember that, okay? Explain how it is possible for the gravitational field strength to be 0 despite the presence of two large masses nearby. So remember that gravitational field lines always point inwards, radial inwards. So these field lines actually have opposite directions. They are vector quantities. So you can actually subtract them. If you add them up, they will be subtracted. Okay. So what's the reason behind this? Gravitational fields from the Earth and Moon are in opposite directions, and the resultant field is 0 where gravitational forces are equal in magnitude. Okay, basically like Newton's third law. At the point where they're equal in magnitude and they're always in opposite direction, right? So they will actually cancel out to give us a net value of 0, and that point will actually be closer to the smaller mass. Now I want to show you something from variant ON21 variant 42. We had a similar sum here. Okay, the neutral point was we were asked to draw a diagram. It was closer to the Moon. So I'm gonna link that up above in the info card. You can see this video if you want. I personally believe that these two variants were a bit more difficult compared to other ones. Okay, it tests you in a lot of cases. Okay, so show that the point at which this happens is approximately 3.5 into 10 power 8 meters away from the Earth. Okay, so we know that the formula for gravitational field strength is gm by r square, right? Or you could opt to write this g is proportional to m by r square, because universal gravitational constant is a constant. It doesn't really matter. So we are going to equate both of them, right? So we get rid of g on both sides. Now r actually represents the distance from the center of the mass. So for Earth it is gonna be x, right? But for Moon it is not gonna be x. What is it gonna be? This distance, 3.84 into 10 power 8 minus x, right? So mass of Earth by x square is equal to mass of Moon divided by 3.84 into 10 to the power 8 minus x whole square. Okay, so the best way to solve these sums, if you want to learn, you did this in AS chemistry in those maths with kp and kc. Remember, if you have x square, it's best to root over both sides. So I input the mass of Earth and Moon over here, then I root over both sides. So I end up with 2.45 into 10 power 12 divided by x is equal to 2.711 into 10 power 11 divided by 3.84 into 10 power 8 minus x. Now what do we need to do? Then we actually cross multiply. Okay, we cross multiply properly. We end up with 2.45 into 10 power 12 into 3.84 into 10 to the power 8 minus x is equal to 2.711 into 10 power 11 into x. This is after cross multiplication. What about this next step over here? I actually skipped a step over here. Why don't I show you the whole thing, right? That would be better, I guess. The next step should go like this: 2.45 into 10 to the power 12 into 3.84 into 10 to the power 8 minus 2.45 into 10 power 12 into x is equal to 2.71 into 10 power 11 x. Okay, so I basically move that to the right hand side. If you add up 2.71 into 10 power 11 plus 2.45 into 10 power 12, we actually end up with 2.721 into 10 power 12, this value over here. Okay, now if you divide it 2.45 into 10 power 12 into 3.84 into 10 to the power 8 divided by answer, you're going to get 345755237, or to two significant figures. Look at our data. We have a minimum number of significant figures of 3.5, right? So we're going to get a value of 3.5, 1 2 3 4 5 6 7 8 into 10 to the power 8. This is what we had to show, right? We had to show this. So for show questions, remember, do not carry forward your calculator answer. You need to use this one exactly for the next one. Okay, let's go to the next one. You have problems in this. Calculate the gravitational potential of point at point P. So you guys are confused about this. Let me clarify. This was present in, I crossed it out by mistake. Wait a second. Wait 1 second. Yeah, better now. So yeah, in ON 2021 variant 4.2, look, they gave us the value for potential. The graph for potential will always be an inverted U, always between two points. There's no other variation. And the graph for field strength will always be like this sigmoid shaped graph. Okay. So what are we tasked to do over here? What do they want us to do in variant 4.1? They want us to find the potential at point P. So for this, we just need to add them up because it's gonna be a negative value. Gravitational potential is always negative. You guys know why. It's a common question, right? It was in variant 4.2. So basically, we know that gravitational potential is equal to minus gm by r, right? So we write that formula. For the Earth, it's gonna be minus 6.67 into 10 power minus 11 into 5.98 into 10 power 24 divided by 3.5 into 10 power 8. And for the moon, it's going to be minus 6.67 into 10 power minus 11 into 7.35 into 10 power 22. Okay. Divided by 3.84 into 10 power 8 minus 3.5 into 10 power 8. Right? Because we need to find out this distance d. That gives us a value of 3.40. Okay. 3.84 into 10 power 8 minus 3.5 into 10 power 8 gives us a value of 3.4 into 10 to the power 1 2 3 4 5 6 7 in 10 power 7, right? So I actually took g common, right? I took the value of g common, and that will actually give us a value of minus 1.3 into 10 to the power 6. We basically added it up, okay, to get this value. Really important sum. So if they ever ask you to find out potential, you just add them up and they will inherently have negative values. All right, really important. Moving on to question number 3. Define specific heat capacity. So two definitions are really important: specific heat capacity and specific latent heat, or just latent heat. Okay. So yeah, for specific heat capacity, it's defined as the thermal energy per unit mass. Right? The thermal energy per unit mass to cause a temperature change of 1 unit, actually. Okay. So in the definition, it says, according to the mark scheme, thermal physics per unit mass, sorry, thermal energy per unit mass to cause temperature change. That's one marking point. Then you need to mention that the thermal energy per unit change in temperature. So I think it's better to define it like this. Specific heat capacity is the thermal energy supplied per unit mass to change the temperature by 1 Kelvin. Alright? It's per unit change of temperature. So for latent heat, what will it be? Is the thermal energy required to change the state of per unit mass without any change in temperature? That's what you need to write, okay? So a sealed container of fixed volume V contains n molecules, each of mass m of an ideal gas at pressure P. Stating expression in terms of V and P and the Boltzmann constant K for the thermodynamic temperature of the gas. So we know that PV is equal to NKT, right? This is the relationship between pressure, small p by the way, pressure, volume, number of molecules, thermodynamic temperature, and Boltzmann constant. So we need to state an expression for T. So make T the subject. We end up with T is equal to PV divided by NK. That's it. Show that the mean translation kinetic energy of a molecule is given by this. This is really common. So we equate PV is equal to NKT, and PV is equal to 1 by 3 nmc square. We get rid of the n's. We end up with 1 by 3 mc square is equal to KT. You cross multiply, get the 3 over to that side, and multiply half on each side. Then we end up with this, right? KE is equal to 3 by 2 KT. Remember that this is the average translational or kinetic energy. It is the energy of one molecule. Explain why the internal energy of the gas is equal to the total K. Typically, internal energy is the sum of potential energy and K of all the particles in a system, given that it is random. So here's the thing. In an ideal gas, there are no intermolecular forces of attraction. So the potential energy of the molecules is actually zero. Okay? So typically, it was supposed to be internal energy is equal to sum of Ke plus the Pe, but since there is no Pe, the internal energy is totally equal to the Ke. Okay? No forces between molecules, no intermolecular forces, or just intermolecular forces are present. Okay? No intermolecular forces between molecules. That's what they wrote. It doesn't have to be like the Mark scheme, exactly like the Mark scheme. You can just explain it. Right? No intermolecular forces between molecules. So potential energy of molecules is actually zero. Now the gas in B is supplied with thermal energy Q. Explain with reference to the first law of thermodynamics why the increase in internal energy of the gas is Q. Okay. So the gas in B, right? Look, the gas in B is of fixed volume. Typically, there are two changes in a gas when you apply heat. If you apply heat, we know that according to the first law of thermodynamics, what happens? The change in internal energy is equal to the heat supplied to the system and the work done on the system. So, work done by a gas has the formula P del V. Since the change in volume is actually zero, work done is also zero. So, all the heat supplied will actually go to internal energy. If the gas expanded, some work would be done by the gas, right? So not all of it would be converted to the change in internal energy. But here we know according to the formula, it's increase in internal energy, increase in internal energy del U is equal to Q plus work done on the gas. Okay. So since it has constant volume, so no work is done. That is why del U is equal to Q. Okay. Now use the expression in B2. What are they talking about? This one. Kinetic energy of one molecule is equal to 3 by 2 kT. And the information C1. All the internal energy is actually equal to the heat supplied to the system Q. So hear me out. Basically, we are supplying Q. None of it is lost. Also, our gas does not have PE. It only has KE. So we are supplying Q, all of it. If you supply Q, all of it is going. So yeah, all the heat we are giving to the system is converted to K, to internal energy, and the gas only has kinetic energy, right? Internal energy is only in the form of K since no P. So Q is actually equal to K. That's the relation if we substitute U in. Okay. Now, ultimately, that's why we can equate these two equations. We can actually equate Q with kinetic energy, and we can write that it's 3 by 2 kT. But remember, this is for one molecule. This is for one molecule only. Okay. So how are we gonna fix this actually? How are we gonna make this for all molecules in the gas? Basically, if you multiply it by capital N, right? If you multiply it by capital N, we're gonna end up with all molecules in the gas. Now look at this. We have specific heat capacity C. Okay. So the heat supplied to the system is actually H is equal to mc del theta. We know that formula, right? It's pretty straightforward. H is equal to mc del theta. So from this equation, we can see that we need to make C the subject. So if you make C the subject, you're going to end up with H divided by m del theta. This is another relation that we're getting. But it doesn't match with this one at the top. Let's see if we can make it match. So H is the heat energy supplied to the gas. H is the heat energy supplied to the gas, which is Q basically. We are supplying Q to the gas. So if you actually substitute Q in the place of H, we are getting this expression. C is equal to Q divided by Nm del theta. So why did I write Nm by the way? Because remember, this mass in H is equal to mc del theta, this actually refers to the total mass of the gas by the way. But our m from this expression, okay, our m here, this is the one for each particle. So if each particle has a mass of m, all particles or the total mass, right? Total mass of the gas will actually be n into small m. Okay, that's why I actually substituted nm over here, and I'm writing del t because it actually matches with the question then. Okay, so in the place of this m, I substituted nm, that's the total mass of the gas, and in place of h, I'm substituting q, and in the place of q, we can actually write n times 3 by 2 kT. Why n times? Because 3 by 2 kT is the change in energy for one particle. So if you do that, you're going to end up with this 3 by 2 del 3 by 2 k del t. Why is it del t? Because we're finding out the change in energy of one particle, right? Into n is actually equal to, is divided by total mass of the gas nm into del t. Okay, so we can actually get rid of del t. We can also get rid of n. What do we end up with? 3k divided by 2m. That's the proof. Okay, so I'm gonna go through it again. Since our gas has no potential energy, only Ke, and we supplied Q to the gas thermal energy, all of it is being converted to internal energy since the volume is constant. So we can equate kinetic energy and Q. But it's the energy for one particle to get the total energy supplied to the system, H or Q, that's going to be equal to 3 by 2 kT, K del T actually, because there's a change in temperature into the total number of particles. Okay, and we also know that H or Q is equal to, let's just write this as Q, that's better. We also know that Q is equal to mc del theta, where the m actually represents the total mass, mc del t, right? Mc del t. So basically this can be written as Q is equal to n times the mass of one particle, right, into c del t. Okay, So why don't we denote this by something else? Let's write capital M then. That would make more sense, right? Total mass into delta. We might see the subject and substitute Q inside, and then we could get rid of everything, right? And we end up with 3K divided by 2M. That's the logic. Now, the container in B is now replaced with one that does not have a fixed volume. Instead, the gas is able to expand so that the pressure of the gas remains constant as thermal energy is supplied. Now, this is a bit complicated. Suggest with a reason how the specific heat capacity of the gas would now compare with the value in C2. Interesting. So, when you heat the gas, beforehand, it did not expand. It was like this. The gas did not expand. All heat you gave was converted to kinetic energy of the gas. Now what will happen? You will supply heat, right? And the gas will actually expand. So not only will it be converted to internal energy, some of it will be lost as work done by the gas since the volume is expanding. Okay. So beforehand, right? Like instead the gas is able to expand, right? So beforehand, suppose we would require 50 joules to cause a change of a certain internal energy. Okay, we would require 50 joules of heat to cause an internal energy change of 50. Now we will require more. Suppose to cause an internal energy change of 50. Okay, we require more energy because suppose the work done by the gas is minus 10 joules. If you did supply 50 joules of energy, the net gain would be 40 joules, right? So if we want 50, what do we need to ensure? We need to supply more thermal energy greater than 50, right? So we need to supply 60. 60 minus 10 is 50. Okay, got it? So let's explain. The gas expands, so work is done by the gas, or the gas does work against the atmosphere or against the external pressure. Okay, now for the same temperature rise, more thermal energy is required. Okay, more thermal energy is required for the same temperature rise. So the specific heat capacity will be larger. That's the answer. They wanted to know how the specific heat capacity would compare. Because for the same temperature rise, just think about it, for the same value of del T, since it's harder to do now, we require more heat. Previously, I told you we required 50, now we require 60, right? As a result, since the numerator is increasing and the denominator is the same, the value of heat capacity will also increase. Okay, that's all. Difficult question. Moving on to question 4. A trolley on a track is attached with springs to fixed blocks X and Y as shown in figure 4.1. The track contains many small holes to which air is blown vertically upwards. Okay. So it's like levitating, right? This results in a trolley resting on a cushion of air rather than being in direct contact with the track. Interesting. So this was a tough one actually. I'm gonna explain this. So let's do this, okay? So the trolley is pulled to one side of its equilibrium position and then released so that it oscillates initially with simple harmonic motion. After a short time, the air blower is switched off. Okay, so initially there is no friction. As you can see, the amplitude is not changing. But when it starts actually rubbing with the track, there is friction. When it starts rubbing with the track, there is friction and damping will occur. Damping will occur, so amplitude of vibration will slowly reduce. Light damping is occurring since gradual decrease occurs. Now, let's try to understand the logic. The length of the spring was initially 20. How do I know this? Basically, look at this. From the figure, the equilibrium position is at 20. See? It's equally spaced. What's the amplitude of vibration initially? 5 centimeter. So what actually happened? This is 20 initially, and suppose it is displaced to one side. It is pulled to one side of its equilibrium. Maybe it was pulled 5 centimeter to this side, then what happened to this one over here? It got extended by a bit, right? It got extended to 25 cm, and on the other side it got contracted and it's 15 centimeter now. Okay, so basically the springs were already extended, do you understand? But we just reduced the extension of one and increased the extension of the other by 5 each. Now determine the initial amplitude of oscillation. So basically subtract 25 and 20, or 20 minus 15. That gives us 5 centimeters. Okay, moving on. The angular frequency of the oscillations. That's basically omega. Omega is equal to 2 pi by t. The time period for one oscillation is, check this out, crest to crest, 4 seconds, right? So 2 pi by 4 is, since we have a minimum of 2 SF, we're going to give our answer to 2 SF, 1.6 rad per second. Okay, so it's 1.6 to 2 SF. Moving on to the next one. What do we have? The maximum speed. The formula for maximum speed is V naught is equal to omega x naught, where x naught is the amplitude of vibration. So 1.6 into 5.0 in centimeter per second, right? So we're getting a value of 7.9. By the way, you need to use your calculator answer, okay? Remember that. And if you're wondering what is the value of speed only, that's just V is equal to omega root over x naught square minus x square, okay? Where x is the displacement at any point. Apart from the quantities in A, describe what may be deduced from figure 4.2 about the motion of the trolley between time 0 and time 24. No calculations are required. Actually, I was confusing this with another question. This isn't that hard. Maybe that was in February, March 2021 or something. We're going to do it later. So, what can be deduced from figure 4.2? Okay. Let's see. So, this figure, right? I assumed one thing in the beginning. That assumption was actually wrong. Okay, so the first thing that we're learning is you cannot make assumptions in physics. What does L represent? It's actually the distance, like the variation with time t of the distance A of the trolley from block X is shown. So it was 20 initially, right? But what happened? At time 0, we pulled it to 25. So this was 20 initially, but at time 0, we actually made it 25. Do you understand? We added 5 centimeter to it. The total is 25 cm. And this trolley, right, we reduced the extension to 15 centimeter. That's what happened. Because why are we doing this? Because L represents the distance from block X. Since at time 0 the distance actually increased, the trolley was actually pulled to the right. Okay, that's the logic. If the graph was like this instead, if it was a minus cos graph like this, at time 0, if the distance became 15, it would be pulled to the left. Okay, so this is what we can deduce, that the initial pull was to the right. What else? The distance from X to trolley at equilibrium is 20 centimeters, right? At equilibrium is 20. This is what I mentioned at the beginning of the question. The time period is 4 seconds actually, right? And the initial motion is undamped because amplitude remains same. So initial pull was to the right. The time period is 4 seconds. The distance from X to the trolley at equilibrium is 20 centimeters. The initial motion is undamped. The motion becomes damped from what exactly? From 12 seconds onwards, okay? The distance, the oscillations or the motion becomes damped from 12 seconds onwards. Remember that, really important. So any three, okay, any three from this. What is the type of damping? Damping is light. And when do we actually reach maximum speed? Always remember, you will have zero speed at maximum displacement and maximum speed at equilibrium, okay, when you hit 20. So when do we have maximum speed actually? So it's here at 1 second, okay, then at 3 seconds, basically whenever we reach equilibrium position, okay, not 4 here, between 2 and 4, right, which is 3. So 1, 3, or you could say that it's stationary at 0, 2, or 4, right? These are available. Stationary at 2 seconds, 4 seconds, etc. So basically maximum displacement stationary, zero displacement from equilibrium position, that's maximum. On figure 4.3, sketch the variation with L of velocity v for its first complete oscillation. So I just told you at maximum displacement, that means at either 25 or at 15, we will have a velocity of 0. These are our first 2 points. And at equilibrium position, that means at a velocity of 20, we will have maximum velocity of how much exactly? 7.9. Okay, so it has to be at 7.9 plus 7.9 once and minus 7.9 once. Then you just join these and you get a figure like this. Okay, so these are your 4 points. 20 plus 7.9, 20 minus 7.9, it's just a bit below 8. Okay, this is minus 6, this is minus 7, minus 8, so it's between minus 7.5 and minus 8, 7.9. Okay, hopefully it makes sense to you guys. At equilibrium position, you have maximum speed, the value we calculated at the beginning. Okay, moving on to question number 5. We don't have this in our syllabus anymore, it's excluded. We don't have this. Digital analog, all of it is gone. Next, 6 is a bit tricky. So here we're dealing with the actual definition of a capacitor. So what is a capacitor? Mainly it consists, the simplest capacitor consists of two parallel metal plates separated by an insulator, which is air here, at a variable distance x apart, as shown in figure 6.1. The capacitance C is inversely proportional to x. Interesting. That's the original formula. It's actually proportional to the area of the plates and inversely proportional to the distance between them. So state expressions in terms of C and V for the charge Q on one of the plates of the capacitor and the energy stored. So we know that Q is equal to CV, right? And energy is equal to half CV square. We need to express this in terms of C and V. We know these formulas. Now listen, this capacitor was charged initially. The charge capacitor is in A is now disconnected from the supply. So it was charged up, alright? It was charged up like this, suppose. And then we just disconnect it. Now, it will remain charged, by the way. Do you understand? Because the charge can't really flow because the circuit is incomplete. Because we disconnected it from the supply. The capacitor will remain charged. Think of charging up a battery. If you take out the battery, does the battery actually lose its charge? It still has charge, right? And the value of the charge will not change. It will stay constant. That's why the new charge on the plates of the capacitor is actually the same as the one initially, CV. But the new capacitance will change. Why? Because after we disconnected it, the plates of the capacitor are initially separated by a distance L. They are then moved closer together by a distance D as shown. The initial distance was L. Now the new distance is L minus D. Okay? So we know that capacitance is inversely proportional to distance. So C into X is a constant. So we can actually say that C times original length is equal to new capacitance into new length, which is L minus T. So if you make the new capacitance the subject, Cn, that is equal to Cl divided by L minus T. That is our new capacitance. But the new charge remains the same. I just told you why. Because since we disconnected it, this charge could not flow anywhere. So the charge on each plate of the capacitor actually remains the same. It doesn't change, even though we brought the plates closer together. Now the new potential difference between the plates. We know that Q is equal to CV and V is equal to Q by C. The charge remains the same at CV. The charge remains the same at CV, but the capacitance changes. It becomes CL divided by L by minus D. Now we can get rid of the C's, and after reciprocal, we end up with V times L minus D divided by L. This is your new voltage. Explain whether reducing the separation results in an increase or decrease in energy stored in the capacitor. This is an interesting question. Basically, it results in a decrease in the energy stored. Why? Because oppositely charged plates attract. Okay? I'm gonna explain the logic. Basically, hear me out. These plates have opposite charge. This is scenario 1. Wait, this is scenario 1. They were further apart, right? So think of it as potential energy. This is an attractive force, just like GP, when we drop an object above the surface of the earth, it falls down. What's the energy conversion? GP actually decreases, K increases, right? So for attractive forces, if objects come closer together, potential energy actually decreases. And the further you take it away, remember at infinity potential is maximum. So the further apart they are, the more energy stored. But if you make them come closer, they will attract more strongly. Since it's an attractive force, so less energy is actually required to separate the charge. Okay, if it was further apart, more energy would be required to separate the charges. We would need to overcome this greater energy, but now it has become easier. Why? Because it's an attractive force. Okay, hopefully that makes sense. You could also see this mathematically. Check this. We know that E is equal to half CV square. Look at the new energy. It's half into the new capacitance CL divided by L minus D into the new voltage whole square V square into L minus D whole square divided by L square. Now if you do the reduction, if you cut the L's and L minus D's, you'll end up with this half CV into half CV square into L minus D by L. Now, this is a fraction, right? And the numerator is smaller than the denominator. So, a fraction has been multiplied with the original energy of half CV square. So, the total energy has decreased. You could also show this mathematically, okay? So, thank God we don't have question 7 either, right? Op amps are excluded. This was really tough. I had it in my time when I gave the exam back in 2018. So, how many questions do we have? Question 8, 9, 10, 11, and 12. Okay, 8 to 12 left. Let's do this. 8 is a tough one. So let's define the Tesla first. Where's Tesla? Basically, they're asking us to define the unit of magnetic flux density. So magnetic flux density, F is equal to BIL, B is equal to F by IL. So if you defined magnetic flux density, it would have been force per unit length per unit current. Now we are just asked to define the unit. So what is it going to be? Newton per ampere per meter. Okay. So it's basically force per unit length per unit current, but in terms of units, and you need to say where the current or wire is perpendicular to the magnetic field, right? This is very important for defining magnetic flux linkage as well. Now, stiff metal wire is used to form a rectangular frame measuring 8x6 centimeters. The frame is open at the top and is suspended from a sensitive Newton meter as shown. In figure 8.1. So current is flowing like this. This was quite a tough one when I did this at first. The open ends of the frame are connected to a power supply so that there is a current of 5 amperes flowing in the direction shown. The frame is slowly lowered into a uniform magnetic field of flux density B so that all of side PQ, the lower side, is in the field. The magnetic field lines are horizontal and at an angle of 50 degrees to PQ as shown in figure 9. Figure 8.2. So these are actually horizontal, okay? Like the figure I drew over here. Okay, like the figure I drew over here. It's actually horizontal. Remember that. So not the one on the right, okay? Not this one. It's basically the one on the left hand side. Not this one, okay? So basically what's gonna happen is use your left hand rule. Use the Fleming's left hand rule. Use your left hand, I mean. Now, since it's at an angle, you cannot take the component that's like, look at the current. How is it flowing? I'm using a blue line. Current is flowing like this. We cannot use the component parallel to current. Do you understand? You cannot use this component. What component do we need to use? We need to use the component that is actually perpendicular to the direction of current. That's why we're gonna take this direction. Okay, by the way, it is horizontal. Okay, like it's not like what it seems, it's actually horizontal. it's not 3D. Okay, so it's actually hard to do. So how are you going to do this? Since we're going to take the component that is perpendicular to that field, so it's actually horizontal like this. This is one plane. Think of a table. This is wire PQ over here, PQ, and the field lines are going like this, right? But we are not going to take that component according to Fleming's left hand rule. Since it's sine theta, we need to take the component that is perpendicular, and the current is flowing like this. So it's father, mother, child. FMS, father, mother, child. F thumb, A magnetic field for index finger, and child C for current, that's the middle finger. Okay, so the middle finger should point to the right. Okay, and the index finger should point into the screen according to my diagram. Okay, so where is the thumb actually pointing? As you can see, the thumb is actually pointing upwards, right? So that's quite interesting. The force is actually acting upwards like this. So they're saying that when PQ is on the PQ of the frame first enters the field, the reading changes by 1 millinewton. We don't know how it changes. Does it increase or decrease? It should decrease. I'll tell you why in a bit. Determine the magnetic flux density in millitesla. F is equal to BIL sin theta. B is equal to F divided by IL sin theta. The force is the change is 1 into 10 power minus 3 newtons, and I is 5 amperes, L is 6 centimeter, right? 6 into 10 power minus 2, and it's sine 50. We get a value of 4.4 millitesla. Okay, so what is the change on the Newton meter? So the Newton meter was actually recording this weight of the frame, right? But it actually experienced a magnetic force upwards. So uh, that value is of 1 millinewton. So it will actually decrease by 1 millinewton because weight is directed downwards, and according to Fleming's left hand rule, we just found out that the force is directed upwards. Get it? That's the logic. Next Starkey. Sorry, next state with reason whether the change in the reading on the Newton meter is an increase or a decrease. I just use my native language basically. Um, so yeah, it's a decrease basically. It's a decrease of 1 millinewton because weight is directed downwards, right? But the force will be directed upwards, which is why it's a decrease because there's an upward force on the wire. Now the last one was really complicated. The frame is lowered further so that the vertical sides start to enter the magnetic field. Interesting. Suggest what effect this will have on the frame. So it's kind of like a motor now. When it actually goes further down, the field lines will actually interact with these sections as well. Okay, the field lines will actually interact with these sections as well. So look at this. Look at what will happen. Okay, so focus. The field lines will interact with this section as well. Okay, it was interacting here at first. It was 50 degrees here. We got this component. Understood? So basically this angle is 50 degrees. Now we need to take the perpendicular component. Current is acting down here 5 amperes. Current is acting upwards here of 5 amperes, right? So here if you take the perpendicular component, just think about it. Use Fleming's left hand rule. What will happen? Here it actually doesn't matter which direction you take. That's totally fine. Like you can actually view it from here. Okay, you can actually view it from this angle because to be honest, this direction is perpendicular to this in a sense. It is at 90 degrees, right? So just make your index finger point that way. Okay, I'm making my index finger because it's already 90 degrees. I'm making it point this way. This is my index finger, and I'm making my middle finger point down. So just do it properly. Point your index finger on the screen that way in this direction. Okay, and the middle finger should point down like this. So where is the thumb pointing? It's actually a weird direction. It's not pointing towards me, but I know that it's pointing somewhere in this direction, right? So it will cause a force like this, something like this. Now let's try it on this side. Here, your index finger should point this way, index, but your middle finger should point up. So index over there, middle finger upwards. Your thumb should point somewhere over in this direction. That's the direction of the force. So for this one, the direction of the force was on this side, something like this. So it's kind of like a motor, right? The forces are actually providing a moment. The forces are actually providing a moment if we think of this imaginary line, and they're actually acting as a couple. So what will these forces do? They will actually cause rotation of the coil, and the rotation will be what exactly? Since the rotation is like this is anti-clockwise rotation, okay? So the forces, since they are of equal magnitude but acting in opposite directions, they will actually cause the frame to rotate. This was a tricky one, right? Interesting. Now let's move on to 9. State by reference to power dissipated in a resistor what is meant by RMS value of an alternating voltage. So this is an important definition. Remember that it is a constant voltage. Remember, Vrms is equal to V naught by root 2. It is a constant voltage that produces or dissipates the same amount of power as the mean power of alternating voltage. Because I don't know if you recall from ON21, October number 21 variant 4.2, we had a question on power. I taught you something. The mean power is actually half of the maximum power. The mean power is actually half of the maximum power since it's symmetrical about that average value, right? So how do you find out average power anyway? We don't use average voltage, we actually use the Vrms voltage. So if you use that constant value of voltage, you are going to get average power. So that's the logic behind this, the definition of Vrms. Okay? So Vrms is a constant voltage that produces or dissipates the same power as the mean power of the alternating voltage. Okay? Now the next one. A coil is rotating freely on frictionless bearings at constant speed in a uniform magnetic field. This rotation causes an induced alternating EMF across the open terminals of the coil. Okay. The induced EMF has an RMS value of 12 and a frequency of 50. The speed of rotation is now doubled. Stirling explained with reference to the principles of electromagnetic induction the effect of increased speed of rotation on the RMS value of the induced EMF. So since we increase speed, the rate of cutting of field lines actually increases. And what happens exactly? Since the speed is doubled, speed of rotation, the rate of cutting will also be doubled. So the maximum rate of cutting of magnetic field lines doubles. So according to Faraday's law, what do we know? The induced EMF is actually proportional to the rate of change of magnetic flux linkage. So since the rate doubled, the induced EMF will also double, right? And we know that V is equal to IR. If induced, since resistance is constant, we assume that if induced EMF doubles, induced current will also double. Okay, so basically the answer is the maximum rate of cutting of magnetic field line, flux doubles or field lines doubles. So the peak and hence RMS EMF and induced EMF also doubles. Okay, so the RMS value of the induced EMF actually doubles. Okay, remember that this is interesting. So if we double the rate, EMF will double, right? The peak value will double, and if the peak value doubles, we know that Vrms is equal to V naught by root 2. If the peak doubles, the value of Vrms will also double. On figure 9.1, sketch the variation with time t of the induced EMF across the terminals of the coil at the increased speed of rotation. Your line should extend from time 0 to time 20. Okay, so let's go for this. Your line should extend from t0 to t20. Initially, we had an RMS value of 12. Okay, we had an RMS value of 12 and a frequency of 50. This is what we had initially, an RMS value of 12 and a frequency of 50. Now, this was before rotation was increased. So using that RMS value, I can find out the original, the OG peak voltage, right? 12 into root 2, that's 16.97 or 17 volts. That was the original peak voltage. But since speed of rotation doubled, this value will also double. And the new peak voltage will actually be 17 into 2, which is 34. So 34 volts is our new peak voltage. Okay, so if you look at this graph, we have 30 here and minus 30 over here. So 34 will be two boxes above, right? So it's over here and here. All right, those are the peak values. How do I know where they're located? Listen, assume that E is equal to 0 when T is equal to 0. We know about this point. Okay, now beforehand we had a frequency of 50. So the time period was 1 by 50, which was 1 divided by 50 into 10 to the power 3. That's 20 milliseconds. We had a time period of 20 milliseconds. Okay. So I actually have a mistake in this diagram. What's the issue? I gave the same time period, but it's not going to be the same. Right? It's not going to be the same. Why? Because we have increased the speed of rotation. Beforehand, we would be completing one period in 20 milliseconds. But now, since our speed has doubled, we know that S is equal to Vt. If speed is doubled, time will be halved. So the new time period will actually be 10 milliseconds. My bad, guys. We had the wrong diagram on the screen. So 10 milliseconds is required for one period. So 5 milliseconds for half, right? So that's the logic behind this. So where will we have our maximum value? It will be between 0 and 5. 1 will be over here. And minus 34 will be over here. Okay. Moving on, we're gonna have this over here again. And 34 here again. So I'm gonna draw the diagram. It's gonna be like this. At time 0, we have an EMF of 0. So yeah, we have something like this. Okay. I messed up. So this is the perfect diagram. Now this was really tough. I underestimated this, but this should be your diagram. Okay. Tell me if you have any other problems. State and explain the effect of the motion of the coil in B of connecting a load resistor across its terminals. So basically we had a coil that was rotating in the magnetic field lines. Now if we connect a resistor, what will happen? Resistance in the circuit will increase, right? So current will flow through the resistor and it will cause a heating effect. So as current will be flowing through the resistor, it actually dissipates some heat energy. Where is this heat energy derived from? The current in the resistor dissipates some heat energy which is derived from the kinetic energy of the rotation of the coil. So over time, the kinetic energy of the coil will decrease, so the coil will stop rotating at one point. So you can either talk about energy dissipation or you have an alternate route. You could go for the current in the coil results in forces that oppose its rotation, followed by this line. This is a common line. Also, I missed a point over here in the last question. I didn't write some extra points. Why does the upward force on wire due to Fleming's left hand rule? Okay, and the frame will rotate so that PQ becomes perpendicular to field. Okay, so after rotation, it will happen in such a way so that we know that the field lines are acting like this, right? So the coil will actually be perpendicular to the field. So it wasn't perpendicular at first, right? It had an angle of 50 degrees initially. So it will rotate in such a way, right? It was like this initially, right? So it will rotate in such a way so that at the end, instead of having an angle of 50 degrees over here, it will have an angle of 90 degrees. Okay, so this is 40, right? So it will rotate in such a way so that it becomes 90 degrees at the end. Okay, moving on to 10, 11, and 12. We're almost at the end. So experimental phenomenon that provides evidence for the particulate nature of electromagnetic radiation. This is basically the photoelectric effect. Photoelectric effect. Basically, photons. Those are particle. That's the particle form of electromagnetic radiation, right? And wave nature of matter. Basically, electron diffraction. We had a question on this in February March 2022. A particle of matter M moves with momentum p. State the equation that gives the effective wavelength of the particle. The de Broglie wavelength. I actually used the wrong pronunciation. I checked it in Google. It's a bit weird, right? He's French, so the pronunciation is difficult. I don't know the exact pronunciation. So mainly lambda. This is the wavelength of a particle. Lambda is equal to h by p, where h is the Planck constant. P should be capital, my bad. And lambda or p is the momentum. Actually, in March 2022, they wrote about momentum, but in this mark scheme they didn't. What is the name of the wavelength? It's de Broglie, right? De Broglie wavelength. Okay, electrons are excited from rest to a potential difference of 4.8 kilovolts. So at the final speed of the electrons is this. Okay, so basically the energy change is gain in K from electric potential energy. K is half mv square. It is excited from rest, right? Is equal to VQ or VE basically, because it's the charge of an electron. So half into mass of electron 9.11 into 10 power minus 31 into V square is equal to 4.8 into 10 power 3 into the charge of an electron, elementary charge 1.60 into 10 power minus 19. So we get a value of V is equal to 4.1 into 10 to the power 7. So this is a show question, so carry this forward in the next part. Lambda is equal to h by p, or lambda is equal to h divided by mv. Lambda is equal to 6.63 into 10 power minus 34. From the data booklet, I have it memorized. 9.11 into 10 power minus 31, right? That's the mass, into 4.1 into 10 to the power 7. Okay. I get a value. I'm getting a value of 9.1 into 10 power minus 19. Since we have 2 SF, wait, I messed up. I messed up the math. One point eight into 10 to the power minus 11 meters. Okay, that's all. Now for 11, sharpness is not in our syllabus anymore. Okay, it's been excluded from 2022, but you should know it's the ease with which edges can be distinguished. All right. Contrast is the difference in the degree or amount of blackening, okay, between two structures. This is in our syllabus. A parallel X-ray beam passes through a thickness of 2.3 centimeters of soft body tissue. The intensity of the emerging beam is 12% of the incident beam. Okay. So there we had an incident beam I naught, and we have I. I is 12% of I naught. I is 0.12, 12% of I naught. So we're going to use the formula I is equal to I naught e to the power minus mu x, where I is 0.12% of I naught. So we can actually write I by I naught is equal to e to the power minus mu x, where I by I naught is equal to 0.12. So 0.12 is equal to e to the power minus mu x, or mu into 2.3. So if you actually apply ln and solve it, you're going to get a value of mu is equal to 0.92 per centimeter. Since this was in centimeter, we got a unit of per centimeter. So in medical diagnosis, X-rays may be used to produce a single X-ray image, or may be used in computed tomography, CT scanning. What are the advantages and disadvantages of CT scanning compared to a single X-ray? Mainly the advantage is it produces a 3D image which can be rotated, right? But the disadvantage is there is much greater exposure to radiation. Okay. Next, last one, finally. What is meant by decay constant? It's the probability of decay of a nucleus per unit time. Okay. A sample of radioactive iodine of mass this has an activity of 2.92 in 10 power 9 becquerel. Determine the decay constant of iodine 131. We know that A is equal to lambda n, right? And we can actually find out capital N. How? Basically, we know the mass. Okay. So they use the formula N is equal to mass divided by nucleon number into U. This is a formula which you can use to find out N, where it's 5.87 into 10 to the power minus 10 divided by the nucleon number 131 into 1.66 into 10 power minus 27. Why is this valid? Because this is the mass of all the particles combined, and this is the mass of one particle. Okay, this is the mass of one particle, 131 into U. You can also use some chemistry. Basically, you can find out the number of moles. How? Mass 5.87 into 10 power minus 10 into 10 power 3, mass in grams, divided by the MR 131, right? You can find out the moles. And to find out N, you can multiply the Avogadro constant 6.02 into 10 power 23 into this answer over here from above. Okay, that would give you the same answer, to be honest. Okay, so you can opt to use this. They use this in the mark scheme. No chemistry. The mass divided by the mass of one particle. So that's 5.87 into 10 power minus 10 divided by 131 into 1.66 into 10 to the power minus 27. We get a value of N is equal to 2.7 into 10 power 15. So lambda is equal to 2.92 into 10 to the power 9 divided by 2.7 into 10 to the power 15. So 2.92 into 10 to the power 9 divided by answer. It's giving me a value of two significant figures, 1.1 into 10 to the power minus 6, 2SF. But wait, our data is given to 3SF. So we should also opt for a 3SF answer. So we should actually write 1.08 into 10 power minus 6. Last one. Suggest two reasons why a detector placed near to the sample in B would record a count rate much less than this per second. So it's like this. This is a sample, right? If you place a detector here, why would it record a count rate that's smaller? Basically, it will not emit in this direction only. It emits in all directions, okay? The sample emits radiation in all directions mainly. Now, some radiation is absorbed by air, right? There's some air between the detector and the sample. Air, or the detector window even. There's a detector window over here. What else? There is some self-absorption within the source, right? There's a last point that's called the dead time of counter, or the inefficiency of detector. Basically, it needs to acclimatize with reading. Basically, like recording temperature. If you record the temperature of two people but do not give enough time for the thermometer to come down to room temperature between the readings, you will get a false reading. So since the decay is happening so fast, the detector doesn't have time to do so. So that problem is called the dead time of the counter, or the inefficiency of the detector. Okay. So this is it. If you have any other questions, let me know. These two variants are super important and super hard. Okay. So I'm gonna link the this was a variant 4.1 or 4.3. I'm gonna link variant 4.2 ON 2021, variant 4.2 up here, and the Feb March paper 2022 paper over here, right? And the playlist for P4 will be linked up over here. And remember to subscribe to the channel and like the content. Okay, keep on supporting. See ya.